Hi students, in this lecture I am going to discuss horizontal settler motion. See list of concepts. First basic definitions, then kinematics. In that we discuss angular and linear quantities. Then dynamics. In that we are going to discuss centripetal force, centrifugal force. Next concept of banking and finally radius of curvature. Okay, let us see. So this is an example for two-dimensional motion. So first we have to focus when we say motion is two-dimensional, one-dimensional. See, for example, a body is moving along the line y equal to 3x. So if you want to know the location of the particle, if we know either x coordinate or y coordinate, any one coordinate is sufficient to know location of the particle, right? Whether we are knowing x or y, one is enough to know where is the particle. That means we require only one coordinate to know the location of the particle. So when we require only one coordinate to know location of the particle, then that is called one-dimensional motion or straight line motion. For example, you just imagine a batsman hitting a sixer. Just imagine a batsman hitting a sixer. Assume the batsman has origin, that location. This is now part of that particle, means that ball. Ball is landing directly in the gallery. Let us take vertically up as y-axis and horizontal as x-axis. Horizontal as x-axis. For example, if we specify height of the ball, if we specify height of the ball, we cannot say or we cannot get location of the ball. For example, I am saying this is a height. You can see for same height, we are having two x coordinates. You can say x1 and one more x2. The ball can be either at this location or at this location. Means just by knowing y coordinate, means just by knowing height, we cannot get location of the ball. Suppose if we mention x coordinate, let us say this is now x coordinate. For this x coordinate, we can have many y values. See carefully. For this x coordinate, we can get many y values. So knowing only x coordinate or knowing only y coordinate, we cannot get location of the ball. Means we have to mention both x and y coordinates. Like here, right? Suppose this is a 2, comma 3. Then we can say what is the location of the ball. If we mention only 2, y can be any value for x equal to 2. If you say like y equal to 3, y equal to 3, x can have any value. So knowing only one of these two coordinates, we cannot get location of the particle. So here we require minimum two coordinates, that is x and y. That's why this is called two-dimensional motion, right? Now coming to subtler motion, when we are saying it is a subtler motion, it is having a center. So first we have to specify what is radius. Secondly, if you measure, if you measure angle made by the particle, or you can say line joining the center and the particle, that line makes some angle with some reference line. If you know that angle, then we can say what is the position of the particle. That means we have to mention r and theta. For example, theta equal to 90, r value 1. Then I can say theta 90 means this is the location of the particle, right? Angle is 90. If angle is 180, this will be the position of the particle because this total angle is 180. So with that with one reference line, we measure the angle made by the radius vector, the line joining center of the circle and the particle that is called radius vector. So angle made by that with that reference line and radius. If we know these two, we get location of the particle. That's why this is an example for two-dimensional motion. Okay, let us see now basic terminology in this one. So it is now horizontal circular motion. Its meaning is circle is in a horizontal plane. That means along vertical there is no motion, only confined to horizontal. Let us see basics of HCM. Let us take this is a circular path and this is center of that circle, and we are taking one reference line to measure angle made by radius vector, angle made by radius vector with that reference line. That is now angle made by radius vector with that reference line, that is theta. Suppose it is now moving anti-clockwise. So when it moves, the angle made by radius vector with the reference line will change. So this theta we call it as angular position. This is known as theta we are calling as angular position. Angular position. And it is measured in radians. Units are radians. Radian. Writing simply RAD. And this has no dimension formula. So simply m power 0, L power 0, T power 0. No dimension formula m power 0, L power 0, T power 0. Now see carefully. The rate at which this angle is changing means the rate of change of angular position with respect to time. That is called angular velocity. I am writing here, this is omega, known as angular velocity. Angular velocity. This is defined as the rate of change of angular position with respect to time. If you remember, while discussing kinematics 1D, we have defined velocity, rate of change of position with respect to time. Now only changes here, angular velocity. This is angular position. Okay. Right. Now from this, see what we can say, units. This will be radian per second. Okay. And coming to dimension formula, it is a t power minus 1 for time. Okay. And we have to focus here regarding this. What is direction part? Direction part will be if motion is clockwise. If motion is clockwise. Motion is clockwise. Then direction will be, it is inwards. Direction is inwards. So we are using here right hand rule, curling fingers along the direction of the along the direction of the particle. So taking the right hand, curl fingers, keeping the thumb along the axis. Now thumb will be into the paper. So it is inwards along the axis. If it moves anti-clockwise, if it moves anti-clockwise, then see, keeping the thumb along the axis, curl fingers along the motion of the particle. It will be outwards, anti-clockwise. It is outwards, or you can say normal to the paper outwards, or normal to plane of the board and outwards. Okay, this is d theta by dt direction part, or sometimes we represent symbol like inwards means cross circle inwards, outwards means it is a dot circle. You just imagine arrow is coming towards us. We can see only a dot. If arrow is moving away from us, means into the board, we can see arrow means we can see a cross mark. So inwards means cross circle, outwards means dot circle. Okay. Like this, we can see direction of omega along the axis. It is normal to the plane of circle. Now we define rate of change of angular velocity. That is, we are calling as angular acceleration d omega by dt. Or writing this as omega d omega by d theta. It is just like kinematics 1D. There we have discussed dv by dt or v dv by ds. Same language. Okay. And coming to here again direction part. For alpha also direction is along the axis. It may be inwards or maybe outwards. Okay. And here, okay, first let us see units. Units are, I think you can guess it, radian per second square. And dimensional formula, it is a t power minus 2. Okay. Now see carefully. If alpha bar and omega bar are in same direction, if alpha bar and omega bar are in same direction, then modulus of omega bar increases. See, the same thing we discussed in kinematics 1D. If velocity vector and acceleration vector are in same direction, speed increases. It is now angular speed. That is the only change. Same way, if alpha bar is opposite to omega bar, then modulus of omega bar, that is angular speed, it will decrease. Okay. So same as the kinematics 1D. Now after having these two, we take one special case like if alpha bar is a constant, if alpha bar is a constant, okay, that means magnitude as well as direction both are constant. Then we can write just like kinematics 1D, here also theta equal to, there we have written s equal to ut plus half at square. This is omega 1t plus a half alpha t square. Next we have written s equal to u plus v by 2 into t. This is omega 1 plus omega 2 by 2 into t. Next, we have discussed one more, that is S equal to, so theta equal to omega 2t minus a half alpha t square. If you remember, S equal to Vt minus a half a t square, that relation. Next, we can write here omega 2 equal to omega 1 plus alpha t. And next, one more, it is omega 2 square minus omega 1 square equal to 2 alpha theta. And next, we have discussed like Sn, right? In the place of Sn, it is now theta n. There we have written u plus a into, it is omega 1 plus, we have taken u plus a into n minus half. It is same, n minus half. So angular displacement in nth second, it is angular displacement in nth second is omega 1 plus alpha into n minus half. So whatever we have learned in kinematics 1D, same thing repeats. So this is now kinematics of SHM in terms of angular quantities. Okay, I hope you got clarity. Let us connect now angular quantities and linear quantities. See once. So how to connect now both linear and angular quantities? Right. Let us see now, first of all, what is distance traveled? Let us initially, particle was at this position. Now it is at this location. If radius equal to r. So distance traveled is nothing but arc length, right? So arc length I'm taking it as S. So S equal to r theta. Let us see now the rate at which distance is covered. That is ds by dt. That is equal to, since r is a constant, in the sense distance of the particle from center is a constant. So r into d theta by dt. Okay, that implies speed equal to, remember this is the rate at which distance is covered, that is speed. Speed equal to r omega. So linear speed, and this is angular speed. Okay, if we differentiate once again, so dv by dt, rate of change of speed. We should be very careful here. Here v is speed, not velocity. Rate of change of speed with respect to time, that is called tangential acceleration. Not acceleration, it is tangential acceleration. So which is equal to r into alpha. So we got relation between linear speed and angular speed. Tangential acceleration, and this is angular acceleration, right? If you want in vector form for v and omega, that can be taken as v bar equal to omega bar cross r bar. Even this is taken as definition of omega bar. So keep this point in mind, right? So we got now regarding velocity vector and omega bar direction, that relation part. Okay. Let us now write equations connecting AT, speed and distance travel. That means kinematics in terms of linear quantities. So here we got in terms of angular quantities. Okay. See once. Right. Let us see now equations. Again, same equations what we have discussed in kinematics 1D. Start from the first one. V equal to U plus AT. But in the place of A, it is now A suffix T, tangential acceleration. So this is now final speed and U is initial speed. So there we have discussed final velocity and initial velocity, right? But final speed, initial speed, in the place of acceleration, it is tangential acceleration. So you have to keep these points in mind. And the next one is equal to ut plus half at square, half at square. Again, is equal to vt minus a half at square. Means same, okay? The same equation here. Next, what I can write here? This is over, right? I think first one is over. Right, this part is left. S equal to u plus v by 2 into t. Okay. Next, what else left here? This last one, right? That is v square minus u square equal to 2. Remember here, this is at 2 as at into s. Distance traveled. If you want distance covered in nth second, Sn equal to u plus at into n minus half. Okay. So kinematics in terms of linear quantities and in terms of angular quantities. Okay. Let us now focus here regarding centripetal acceleration. So here we are saying that motion is in circular path. Circle means direction keep on changing. Direction keep on changing. And when we are saying AT, rate of change of a speed, means acceleration. Tangential acceleration is along the tangent. That's why name is tangential. This is along the tangent. So because of this, only speed is changing, but we are knowing that its direction also changing continuously. So there must be another component of acceleration because of which its direction is changing. Okay. Let us focus how to get it. That is known as centripetal acceleration. See, calculation of centripetal acceleration. Centripetal acceleration. See, I assume that at one point of time, its radius vector making an angle theta with reference line. Its radius vector makes an angle theta with radius vector. Okay. Now let us consider small time interval dt. Let us consider small time interval dt. So small time interval dt. In small time interval dt, we can say that speed is almost the same because dt is very small. Suppose speed is v. So speed remains the same because it is a very small time interval. Let us take this angle changes by d theta in that small time interval. Radius vector rotates by an angle d theta. Okay. Now we have to find centripetal acceleration. Acceleration means see what we can do. First focus change in velocity vector. V2 bar minus V1 bar. Since we have taken dt very small, speed almost the same. Therefore, this modulus value will be equal to 2v sine d theta by 2. Recollect once in vectors we have learned if we have two vectors, I am writing here, if you have two vectors of same magnitude, then p bar minus q bar equal to 2p sine theta by 2. If you remember, right? So I have taken same thing here. 2v sine angle is d theta. So d theta by 2. Then see how much we get. Since angle is very small, d theta by 2 very small. So sine also very small. So when angle is very small, sine d theta by 2 approximately equal to d theta by 2. If you remember, we have taken number of times that whenever theta very small, sine theta approximately equal to theta. So take now that approximation here. Now 2 and 2 gets cancelled. This is equal to v into d theta. This is now change in velocity vector modulus value. If you differentiate that, dv by dt, or you can say it is not dv bar, okay? Then what we get here? D theta by dt. Then that will be, see that will be what we can write here. We have taken it is, we got v into d theta. This we got v into d theta by dt. In the place of d theta by dt, we can write omega. So v omega. Or we can write in the place of omega, v by r. Okay. So this is also written as v by r. It becomes v square by r. Or we can write this in terms of r and omega. That is r omega square. Okay. That means this centripetal acceleration is equal to v omega or v square by r it is r omega square. Its direction is towards the center. I am writing here. So whenever a particle is in circular motion, it is having two components for acceleration. It is not two accelerations, two components of accelerations. Okay. Acceleration having two components. One is AC, other one is AT. Now this is the resultant. So whenever you want to calculate acceleration, then we have to focus what is a tangential acceleration, what is a centripetal acceleration, then we have to take resultant of those two. So between these two, angle is always 90. So we can write modulus of the acceleration is square root of AC square plus AT square. Okay. If they ask question like what is angle made by acceleration vector with tangent, then I can say suppose that angle is taken as beta. I am taking that angle as beta. Then I can write here tan beta equal. This is what we have learned in vector set. AC and AT are two vectors which are mutually perpendicular. Now A is resultant of those two vectors. Angle made by the resultant with AT is given by AC by AT. So we can expect many questions basing on this result. Okay. So this is now regarding kinematics of horizontal circular motion. Okay.